Right. This is stoichiometry part 2 and explores certain experimental issues associated with it. In stoichiometry, the key idea is to realize we can't lose any atoms, we can't gain any atoms. All the pieces matter. So what kind of issues are we going to try to solve here? There are issues of limiting reactants, issues of percentage yields, issues of coefficients, and chemical formulas. Now here's a working analogy. If I have 8 car bodies and I have 48 tires, the ratio is for every 1 car I use 4 tires to make 1 full complete car. Now if you work this out, I can make 8 complete cars because after I make 8 cars I have no more car bodies. However, you will notice I still have 16 tires left over. What do I do with those 16 tires? Nothing. They still stay there. They're still accounted for. We got to make sure all the pieces are accounted for. But we would say that the tires are in excess. So tires are the excess reactants, and the limiter for how many cars you can make is the car body itself. So in theory, we can make 8 cars if we have the starting material shown. When we use the word reactant, it does mean the same as reagents used in chemical reactions. So the limiting reactant or reagent is the one that is consumed first. It sets the limit on how much you can produce. Let's take a look at this diagram. You'll notice that on the left in that box we have 2 reagents, the green one and the red one. You can think of them as molecules. So the green molecules and the red molecules are going to become connected. And when you do, on the right, you will see that all the greens are connected to red, but there are reds left over. So we will consider the red molecules to be in excess. Now, how do we figure out which is the excess? What we have here, NO, nitrous oxide, bonds with oxygen, will produce nitrogen dioxide. Now, on the box on top, you will notice we have red and blue molecules. Those are the NOs. And of course, we also have the 2 reds bonded, and that's the O2 molecule. Now, when we do a chemical reaction, you might recall from John Dalton, the way to conceptualize it is all the molecules in the upper box all fall apart into separate atoms. So you'd have solo red, solo blue. What happens is those atoms come back together in a different combination. In this case, as you can see, the result or the products are 1 blue, which is 1 nitrogen atom, and 2 oxygen connected to it. Those are the red atoms. And the overall blue with 2 red, that's the molecule nitrogen dioxide. But you'll notice that there are some O2s still there. And the answer is because they're not consumed. We run out of the NO and cannot then consume the rest of the O2s. So the O2 is considered in excess. Now, can we, in fact, they're shown there, can we, in fact, figure out which is the excess and which is the limiter? Can we do that in terms of equations and not have to draw them out? And the answer is absolutely. That's the basis of stoichiometry. Now take a look at this one. The reaction takes place, it's the same one, but if you look towards the bottom, there is no O2 left over. There is no NO left over, meaning that all the reactants are completely being consumed. Now, when that happens, we call that initial condition a stoichiometric mixture, meaning you have the exact amount that you need for each reactant to be fully consumed. Now, there's another item here called percentage yield. And percentage yield says how much do you actually produce during the reaction. Stoichiometry gives you, in theory, the maximum amount, but when you actually do it, how much actually gets produced. And that's referred to as the percentage yield and the effectiveness of the reaction. So the actual yield is the amount that gets produced when you actually run the reaction in a test tube. So the equation says that the percentage yield is the actual divided by theoretical times 100. And that is an equation we want to make sure you're aware of. Now, as it says, all reactions in reality never give you the amount you should have. Why is it always less than 100%? Well, you may not have measured out the reactants properly. The reaction doesn't go to completion. LR, limiting reagent, does not get completely consumed, or it reaches a state of equilibrium, which is an idea that's coming up in a couple units. And sometimes it might go beyond 100%. How is that possible? You simply have impure or contamination going on. So you should never get more than 100% because you cannot get more than the limiter, but sometimes it does happen. Now let's run some calculations of percentage yield. So we're going to react in this reaction. We're going to work with C3H7OH, and we're going to work with O2, and it's going to produce supposedly 82.34% of CO2. So how much are we going to collect here? Well, the percentage yield is actual over theoretical. Theoretical is 2.3013 moles, or 101.28 grams of CO2. If I have 82.34, it's actually 83.39. Now, how about on this one? Let's take a look at calculation of the limiting reactant. If you run the calculation and actually do the stoichiometry, the theoretical yield is 256.7 grams of iron. Now, wait a minute. Where did we get 256.7 grams of iron? We ran the stoichiometry, the daisy chain or train tracks for the reaction that is given, and we ran and got a calculated result of 256.7. However, I actually only get 53.1. So the question is, what's the percentage yield? 20.7%. Now what that means is this reaction is not very successful. It only produces 20.7% of what should have been produced. And why that is based upon a unit that's coming up. Make sure you're always careful as to who you have kicking the ball.